So let's start the presentation. So welcome everyone to this session on how we can test our code as a crime scene. And first, a little bit of history. So this presentation is based on an earlier session I did a couple of years ago called Treat Your Code as a Crime Scene, and that session was targeting developers. So I have a developer background, so I come as a little bit of an outsider to the testing field. However, over the past years, I've been fortunate to work with many really skilled testers, and I've also been part of a research project on test automation for 3 years. So this is an area of interest to me, and that experience also gave me plenty of opportunities to see how we can take the crime scene techniques and apply them to a testing context. And that's what I would like to share with you today. So I'm going to start with a brief introduction. After that, we're going to explore the problem space, trying to understand why is it so challenging, why is it so hard to develop and test large-scale software systems. After that, we're going to move on and explore some possible solutions, and we will take inspiration from a very different field. I'm going to define and explore a topic called behavioral code analysis, and I'll tell you what that is in a couple of minutes. And finally, I want us to move beyond code. And what I mean by that is that we're going to use organizational patterns, structures of how we as a development organization are organized to predict where our bugs will be. That's my favorite topic. And of course, I'm going to leave plenty of time for questions. And along the way, I'm also going to introduce some tooling options for you so that you can automate the stuff I'm going to talk about today. But first things first. In this presentation, I'm going to make a lot of references to different branches of psychology. And you might, of course, ask yourself, why do I, as a software developer, why do I feel qualified to talk about psychology? And I think it's a fair question. So let me tell you a little bit about my background. I got my first professional software development job on August 1st, 1997. And I say professional because to me, it was simply someone starting to pay me for what I used to do for free, write code. So I actually started out programming in the late 1980s on my Commodore 64, a wonderful machine. So at the time I joined my first job, I already had close to a decade of programming experience. So I thought, this is going to be pretty easy, right? I know this stuff, I know how to write code. But I was in for a really rude awakening, because it turned out that large-scale corporate development is a very different beast. It's very different compared to what I had been doing on my own. And I noticed that already the first day in my new job, I noticed that things were radically different. For starters, the first thing I noticed was that no one really had time to onboard me. No one had time to show me what to do. No one had time to show me what to work on or how the system fit together. This was a large system. And the reason for everyone being so busy and not having time for onboarding was because they were just wrapping up a really large development project. So this was a project that involved both new hardware and several new software subsystems. And that development had been going on for years. And by the time I joined, they were wrapping 8 months development iteration. So 8 months of development by 5 to 6 different teams. But fortunately, everyone promised me things are going to get better now, because in this large project, there's only a single thing left to do. I repeat, there's only a single thing left to do, and that is to integrate it. And to make it better, that integration phase was planned for the duration of 2 weeks. As you can imagine, it didn't went exactly to plan. So in fact, after 6 months, the whole project had to be cancelled, replanned, rescoped, and restarted with partially new staff. And this was my introduction to large-scale corporate development. And I have to tell you, from there, it just went downhill. So at some point, I thought, I wanted to understand, why do we end up like that? Why do so smart people, because there were a lot of really smart engineers, even the occasional smart manager on that project. So why do they keep making decisions like that, right? 8 months of development, 2 weeks of integration. And I kind of understood that I won't find the answers to that within the software industry. So I decided to look elsewhere. So I picked up psychology. And I spent 6 years at the university studying psychology, so I have a master's degree in psychology. And at the same time, I worked full-time as a software developer, as a consultant, and that gave me plenty of opportunities to take what I learned in psychology and apply it to technology. And I've been writing 2 books about this intersection of psychology and code. Your Code as Crime Scene, published 5 years ago, and my new book, Software Design X-Rays. And we're going to touch upon some of those topics in this session. All right, more than enough about me. Let's move on and explore software. So I want to start this talk by covering the challenges of large-scale software systems. Because of more than 2 decades of the software industry has taught me anything, it is that large software systems are incredibly complex to understand and reason about. And I think the main reason that it's so hard to reason about large-scale code bases is because software lacks visibility. We don't have anything like a physical software, right? So there's no way we can take a large software system, pick it up, turn it around, inspect it. There's no way of doing that. And the consequences is that we often end up making decisions without having the whole picture, without having accurate situational awareness. And this is something that's pretty well known in psychology. And psychologists talk about something called the law of expectations. And the law of expectations is that we humans, whenever we lack certainty about the world, our conscious experience is heavily determined by unsupported expectations. Or, put in a better way, by my favorite psychologist, Barthes, he claims that humans seems to be driven at least as much by fantasy as by reality. And what this means in practice is that when working with large-scale software systems, a lot of our decisions are actually driven as much by fantasy as by reality. Does it really have to be like that? Well, I'm going to show you some possible alternatives soon, but before that, I'd like to clarify this point and really drive it home. And I like to do that by taking you to another experiment. This is from the field of psychology again, an experiment done in the 1970s. And this is one of my favorite experiments, because what researchers did here was that they asked 2 different groups of people. One group located in the south of England, and the other group located in the north in Scotland. They asked them to draw a map over Great Britain. And this is the 2 maps that the group came up with. Can you guess which map was drawn by the group in the south? Yeah, that's right, the one to the left. And you can pretty much see that the group in the south, they kind of exaggerated the distances in the south, which happens to be the area that the participants are the most familiar with. And the group in the north, they made the opposite error, right? They underestimated all the distances in the south and tended to emphasize the parts of their geography that they were familiar with. So again, this is our experience, our prior experience kind of influencing how we see reality. This is something I see on software systems all the time. I mean, today's software systems are incredibly complicated. We might have multiple different subsystems that we need to integrate, that need to exchange information. And of course, we also have an increasingly more complicated surrounding world, which means we quite often have different user spaces, right? And different user-facing applications like Android. We might have an iOS app, we have a desktop app, we have REST APIs to integrate with other systems, and so on. And the question is, of course, if we have a complicated system like that, and we are responsible for making sure it works, right? And it serves our users correctly, how can we pick up that code base and find out if there are any weak spots in that system? I mean, given a complicated system, where are the most risky areas? Where are the parts of which with defects? And to us working as testers, we also have the additional challenge that the system will change all the time. All successful software evolves. So a software system is always a moving target. It changes all the time. And the question for us is, of course, how often do we retest everything? Do we really have to retest everything? And perhaps more important, do we want to? I mean, our time is limited. And we can, of course, automate, right? We can automate a lot of our checks and verifications. But do we have to automate everything? Do we want to automate everything? And when we start with test automation, where do we start, right? If we have 2 million lines of code, where do we focus our efforts? These are challenges that we have been trying to tackle in the software industry for a long, long time. And one avenue that I've seen that is quite popular that I want to cover is metrics to decide not only what to test, but also to decide where to write automated tests. So the reasoning here is that we know that factors like code complexity, and code complexity for the sake of this presentation simply means code that is hard for a developer to understand. And if the code is hard to understand, it's very likely that we developers will make a mistake when we modify that part. So if we knew the code complexity of each piece of code, maybe we could use that to guide testing, right? And when you start to look into things like code complexity metrics, you will find that there are many different metrics. The most popular one tends to be cyclomatic complexity. I'm going to keep this pretty brief, but cyclomatic complexity, basically, it's an old metric from 1976. And the way cyclomatic complexity works is basically that it considers each function in your program. It's a function level metric. It considers each function, looks at the number of logical paths through it. And a logical path is simply an if statement, a loop, and so on. And then you sum up the number of logical paths, and you have your complexity number. And the higher that number, the more complicated the code is. So maybe that sounds simple enough, right? Maybe that could be something we can use to guide testing and improvement efforts. Well, if we look at actual research, we reveal a pretty dark picture. So let me read one of my favorite quotes on metrics for you. Syntactic complexity metrics can cover the whole picture of software complexity. And what's so fascinating about this quote is that it's from two researchers. What these researchers did was that they took a bunch of well-known complexity metrics, cyclomatic complexity being one of them, and then they looked at how good are these at predicting real issues, right? Really complicated code. And what they found out was that the moment they start to control for the number of lines of code, those more elaborate metrics like cyclomatic complexity, they don't add any further predictive value. Wow, number of lines of code. Is that the best thing we can do? The current state of the research suggests that. But number of lines of code, it's a really rough metric, isn't it? It is. And I think a reason for that is well captured in the next quote I want to. This is a quote from Robert Glass, one of my favorite authors when it comes to software engineering. And Robert Glass, he claims that the use of metrics to manage software projects has not even reached a state of infancy. And this kind of sounds a little bit cynical, but in my experience, it's definitely true. And I like to add and weigh in myself on this discussion of how good complexity metrics are. Because one thing I've seen over and over again is that the problem I have with complexity metrics is that they lack context. What do I mean by that? Well, what I'm referring to is that complexity is really only a problem when we need to deal with it. So we might have a large software system, we might have an overly complicated part over here, but if that part has been thoroughly tested and verified 2 years ago and haven't been touched since, and nothing in the surrounding calling context has changed, is that really a problem? Should we really spend time verifying and improving that part of the code? Probably not. So if complexity metrics don't work to guide testing, what should we do instead? Well, what Robert Glass is something different. Glass suggests that we should use our intuition. And I have to tell you, as a psychologist, you really have to love the concept of the intuition, because you know it's such a warm, fluffy human subject. But I have to say that this psychologist, I'm not convinced that intuition will help us. And the reason I say that is because intuition has some main limitation. Intuition just doesn't scale. Because there's no way no matter how experienced we are or how skilled we are, there's no way we can pick up a system with million lines of code and scale our intuition to it. It's simply impossible. Because as I pointed out earlier, a software system at that scale under active development is a moving target. So it's impossible to keep up with it. So what can we do instead? Well, when I struggled with these challenges myself during my consultancy years, I was also in the middle of my psychology education. And I decided to take inspiration from a radically different field, a different discipline, but one that faces similar, open-ended and complicated questions as we do. So, welcome to forensic psychology. I would assume that some of you have a little bit of experience with forensics. I mean, maybe you get exposed to it via media, maybe you read about it in the news, or maybe you've seen TV series like Dexter, right? That's forensics at its finest. Or maybe you have watched CSI. Or perhaps you have seen one of my favorite movies, The Silence of the Lambs. Can you remember that movie? It's And I have to admit that the first time I watched The Silence of the Lambs, I got really, really influenced by Hannibal Lecter. And yeah, I mean this in a non-scary way, right? I was influenced by his forensic skills, not the other stuff. So if we ever meet in person, I promise you it's completely safe to have dinner with me. So the reason I got fascinated by Hannibal Lecter was because if you think about what he does in that movie, it's pretty fascinating. So Hannibal Lecter, he sits there locked up in his cage, and he receives information about the crime scenes. And based on that information alone, Hannibal Lecter is able to deduce the personality, but also the motives of the offender. And when I saw that as a kid, I was like, wow, I want to learn to do that. Years later, when I actually started to study forensic psychology at the university, I got terribly disappointed. Because it turns out the techniques that Hannibal Lecter had been using, they have a pretty severe limitation. It turns out that Hannibal Lecter's techniques only work in Hollywood movies. So fortunately, there are some much more scientific methods that I would like to expose you to. And then we're going to see how we can apply the same techniques to software. But I think it's important to cover the forensic stuff because it gives us the mental framework. So let's have a look at the scientific method called geographical offender profiling, which is radically different from what you see in Hollywood movies. So when I started to study geographical offender profiling, I got pretty surprised. And the thing that surprised me the most, maybe because it's so obvious. So let me check this with you. Did you know this? Did you know that criminals, most of the time, behave just like us? As a criminal, they might go to the movies, right? They go to the restaurants. They go shopping, right? They need to buy groceries. Maybe they even pick up the kids from school. So the thing is that most of the time, they are not criminals, right? They're acting like any normal person. And this is important because what this means is that when a criminal moves around in a city, that's typically where they spot opportunities for crime. And the reason I say this is because for a crime to occur, there has to be an overlap in time and space between an offender and a victim. And what this means to us is that the crime scenes, their geographical locations, are never ever random. They contain information about the criminal. And that's something we can use to catch them. So let me show you how this works with a real-world case study. So let me take you back in time to 19th century London, to the Whitechapel area, the streets that Jack the Ripper haunted. So what you see on the screen here is a map over Whitechapel, the way it looked 130 years ago. And you see those blue dots. 5 of them represents the crime scenes of Jack the Ripper, those victims. And the 6th one represents a piece of graffiti that was painted on wall, where the very likely person responsible for that was Jack the Ripper. So what you do in a geographical offender profile is basically that you take each crime scene and you consider it as a center of gravity. And they kind of weight all those crime scenes together mathematically to come up with a new center of gravity. And if you look at this map, you see the red area in the middle. That's what's referred to as a hotspot. And according to the research, 8% chance that our offender will have his home base there in the hotspot. So how can you use this? I mean, Jack the Ripper, he was never caught. So how do we know if this profile is any good or not? Well, let me reveal to you who I think Jack the Ripper was. Let's look at my favorite Ripper suspect and see how well he fits the profile. My favorite suspect is Mr. James Maybrick. So James Maybrick was a cotton merchant from Liverpool, and when he went to London to do business, he used to rent a room in the Middlesex Street. So let's have a look at where Middlesex Street is in this hotspot. You see, Middlesex Street is located right in the middle of the hotspot. So what this would mean to us if we were investigating Jack the Ripper is that James Maybrick is a pretty good fit for the profile. So maybe we should prioritize James Maybrick over other suspects. And the first time I learned about geographical offender profiling, I was like, what if we can do the same for source code? What if we could pick up that large software system with millions of lines of code and narrow it down to a few hotspots? Because what a geographical offender profile does for investigators is that it takes a potentially vast geographical area and narrows down to a much smaller part where we can now focus our manual expertise. Maybe that's the area to patrol and supervise and still be pretty sure that we get what we want. So if we could do the same for code, that would be a big win, right? We can narrow those systems down to a few hotspots and know that if we focus our testing efforts here, our verification efforts here, we're very likely to get the biggest bang for our bucks. So how could we use this in code? Well, the first thing we need is some kind of behavioral data. Obviously not over criminals, but over developers. How do we developers move around in the code base? How do we interact with the system we're building? And it turns out we all already have all the behavioral data that we need. We're just not used to think about it that way. I'm talking about our version control systems. And you see a simple example from Git here. Our version control data is a virtual goldmine. So if you look at the version control system, your version control system will know exactly which developers that worked in which parts of the code and when they did it. So that's our geographical locations. What's even more fascinating with version control data is that it's also social. So our version control system knows exactly which developer that wrote which piece of code. And this is something that we're going to use later in this session to see how we can identify organizational patterns that predict defects. So let's get specific here. Let's move on and look at an actual case study. I want to show you a real geographical offender profile of code. And for this first case study, I like to present a code a lot of you might actually carry around in your pocket as I speak. I'm talking about this. I'm talking about Android. More specifically, I'm talking about part of as the platform framework base. So the platform framework base is a pretty large code base, approximately 3 million lines of code. And that code is written by more than 2,000 developers. And this is what the hotspot visualization looks like. So how do you make sense of this visualization? Well, the first thing is, if you look at those large blue circles, the ones that blink on screen right now, you will recognize each one of them is a top-level folder, right? So this is a hierarchical visualization that follows the structure of your code. So if this was your code base, you would recognize the name of those folders as a top-level component or a subsystem or a top-level service, something like that. It's an interactive visualization so that we can zoom in to any level of detail that we are interested in. And once we get to the lowest level, we see that each file with source code is visualized as a circle. And you see that those circles, they have different size. That's because size is used to represent code complexity. So how do I calculate complexity? I told you a couple of minutes ago that there are measures for it. That's true. So I do calculate code complexity, but let me assure you once again that code complexity is the least important dimension here, right? So I recommend use whatever you have easily accessible. If you already have tooling in place to calculate cyclomatic complexity, by all means go with that. If you don't have anything, then use a simple count of the number of lines of code, because again, this is not the most interesting dimension. To make code complexity actionable and interesting, we need to put it into context. We need to figure out, does this complexity actually impact us? And one way of doing that is by looking at the change frequency of each piece of code. And this is data that we can pull out of Git. So we can simply look at the changes done to that file and see the more often that code is changed, the more red it becomes. So a hotspot here is simply when we combine these two dimensions to identify complicated code that has to be worked on often. Those are our hotspots in code. So by using the hotspot criteria, we can quickly identify and shrink our problem space, defined as the large code base, into a number of hotspots, where we can now focus more detailed testing and verification efforts. And in a large system, the hotspots typically make up 2, 3, maybe 4% of the total code base. So it's already a big win to be able to prioritize like that. But we can do even better. We can identify specific high-risk areas in the hotspots. And to do that, I use a concept I call code health. And the reason I talk about code health, not something more common or general like quality or high-quality code, is because I really dislike the word quality when applied to source code, because quality kind of suggests different things to different people, and quality also kind of suggests an absolute. And in my experience, that's not always the case. Code quality is contextual. So what I do when I reason about code health is simply to find out how healthy is that code from a developer perspective. Because with code that's of lower health, it's simply going to be more expensive and more risky to make modifications to that code. And to me, code health is not a single thing. It's a combination of factors, and I have listed some of them here on screen. So what I do here is simply that I look at the number of patterns that are known from research to correlate with the increased maintenance costs and an increased risk for defects. So one of the things I look for in a hotspot is low cohesion. So low cohesion simply means that that hotspot has accumulated too many responsibilities. So maybe it's involved in implementing 4 or 5 different features, right? So this is often a reason why hotspots become problematic, because with many different responsibilities in the same code, it's also going to have many reasons to change. And that in turn means that many different developers are likely to work in parallel on that code, which puts you at risk for things like unexpected feature interactions, which are some of the worst bugs you can ever have. Another thing I tend to look for is a concept called deeply nested logic. So it's a kind of a complexity metric, but very different from cyclomatic complexity. So let me explain it to you and why it's a problematic pattern that you want to be aware of in your code. It all boils down to a concept called working memory. So working memory is a cognitive area in your brain, and working memory is what you use to perceive, interpret, and manipulate information in your head. So it's working memory that you use when you solve crosswords or solve a Sudoku, or when you read code. So working memory is vital to all software developers. The bar that working memory is also a strictly limited cognitive resource. There's only so much information we can hold in our head at once. And modern psychological research paints a pretty dark picture. It might be as few as 3 to 4 items that we can hold in our head at once. And this is risk when we see code like this. So I have a look at this brief code snippet. It's a piece of code I picked out of React from Facebook, a JavaScript library. And let's pretend that we want to make a change to the code as indicated by that arrow. Now, that arrow is nested. First of all, it's nested inside a switch case. So that's one logical state that we need to keep in our head. We're in a specific state there as defined by the case. And under that, we see that 1, 2, 3 if statements nest together. And each one of those conditionals basically represents a state, which means that's information that we need to carry when making that change. So what this information means is that with nested logic like this, when we make that change to a code, we need to keep not only 1, 2, 3, but 4 different things in our head when making that change. And what that means, given what I just told you about the limitations of working memory, is that we're making change to that code. And we're making that change with having our cognitive working memory already overloaded to a maximum. So it's no wonder that things go wrong. And in fact, if you look at research, you will see that factors like deeply nested logic are responsible for roughly 20% of all programming mistakes. So this is something we definitely want to be aware of if we have it in a hotspot, because it's going to impact correctness. A related pattern that I want to cover briefly is something I call the bumpy road code smell. It's related, but not the same. The bumpy road code smell is when you have chunks of deeply nested logic and you have multiple of them within the same function. So it's like an exaggregated version of deeply nested logic. It's usually much more problematic when you find this pattern. So that's another thing I want to be aware of. And if you want to read more about the bumpy road code smell and complexity metrics in general, then I have a new blog about it called Complexity in Context that's referenced here on the slide deck that you should have access to. All right, so I hope you find it interesting so far. What I want to share now is some of the experience that I've learned of applying these techniques to real-world, large-scale software projects. The first challenge with using hotspots to guide things like testing or guide test automation is that you have to be aware of how far back in history you travel to gather information from your version control system. Because in my experience, hotspots, they tend to stay where they are, right? So code that was problematic 2 years ago is likely to still be a problem. Code isn't refactored as often as we would like it to be. But what this also means is that occasionally you might find a hotspot that was problematic a couple of years ago, but it has since cooled down and attracts much less development activity. And you don't want those old findings to kind of bias more recent results. So one technique that I found works really, really well is this. So a couple of years ago, I worked with a really great team of testers. They were spending most of their time automating different test cases on all kinds of levels. But at the end of each iteration, we worked in first 2 week and later 1 week iterations. They tended to do some exploratory testing. So they typically set 1 or 2 days aside to do exploratory testing. And that exploratory testing provided extremely valuable in identifying a lot of stuff that we couldn't catch with automated tests. And they used hotspots to guide that exploratory testing because their time was limited, right? So what they did was they used sliding windows equal to the length of the iteration. So when doing 2 weeks iteration, they had a sliding window of 2 weeks and calculated hotspots over those 2 weeks. So they know that, right, this is code we need to focus our testing efforts on. And using the sliding window technique to analyze the hotspots in the recent iteration or sprint, you can again take that large system and narrow it down to something that's truly actionable. Another thing I learned was that hotspots, the way I have showed them to you now, are on the file level. But when testing a large system, you're typically interested in a higher level abstraction. You're not necessarily that interested in individual files. You're more interested in high-level components or services or subsystems. So what I want to show you now is to take the hotspot concept and scale the system level. And I want to show you how this looks by turning to a different code base. So what you see here on screen is Spinnaker. And Spinnaker, for those of you who aren't familiar with it, is a cloud-based continuous delivery platform created by Netflix and maintained by Netflix and Google. It's open source. And the cool thing with Spinnaker is that it's a microservice system. I'm not sure about the micro prefix. Some of those services are truly pretty large, but it's a service-based system anyway, so it's a distributed system. It's also located in more than 35 different Git repositories. So basically each service resides in a specific Git repository. And they are implemented in many different programming languages. There are 7 different programming languages. So this is a true Blot code base. And the first thing I want to point out to you, that you can see this in this, that hotspot visualization, is that hotspots are language neutral. And that's because the hotspot concept isn't based on code. It's based on version control data. A version control data is language neutral. We can get that holistic overview and use this technique no matter what programming languages we use. Another thing that we see is that we can of course start and reason about hotspots here on the file level, but again, I want us to climb up the abstraction ladder. So what I do when I have these complex code bases is that I introduce the concept of architectural components. So I basically take the folder structure and then I map the content of different folders to logical names. And the names I map to should be something that carries a meaning in our architectural context. So in the case of Spinnaker, they have this microservice. So I basically map each Git repository to a logical name, which means I take all the code and combine it to get the complexity dimension. And then I take all contributions done to any file in that Git repo and I aggregate them to come up with hotspots on an architectural level. So this is what the same hotspot analysis looks like on an architectural level. So each one of those circles, they now represents a whole microservice or a subsystem. And this reveals a much more interesting initial view, because we now immediately see that if we want to focus testing or verification to anything, we should definitely focus to the deck component. Because deck that you see there to the left, that's where like the majority of all action have been over the past iterations. So that's the part that really could benefit from our increased engagement. And from here, I can now, if I want to, I can do a hotspot content in deck and reveal the file level hotspots, so I can narrow down my testing efforts even more if I want to. Now, I have already covered a lot of ground here for you, but I want to talk a little bit more about hotspots because I really want to communicate why they work so well. And I've tried to go along, but let me show you a very different view of hotspots. So have a look at the following graphs. All these graphs, they show exactly the same thing. On the x-axis, you have each file in the system, and those files are sorted according to the change frequency. That is, how many changes, how many commit have the developers done to that file. And the number of changes is what you see on the y-axis. If you look at the top level row, you see that there's an example from 3 radically different code bases. 3 code bases implementing different programming languages, targeting different domains, developed by different organizations, different developers, different lifetime spans. Everything is different, right? And still, they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single code base that I've ever analyzed. And I probably analyzed somewhere between 250 and 300 code bases by now. So this seems to be a general rule for how software evolves. And this is important to us because what it means to us is that most of our code is going to be in the long tail. So that means it's code that's rarely, if ever, touched. Most development activity, on the other hand, is going to be a relatively small part of the code. So what the hotspots do is that they identify those parts of the code so that we can focus improvements, maybe even prioritize test automation to those parts of the code that are likely to need it the most. Now, when I start to work with hotspots, I wanted to make sure that I could somehow measure and put some kind of quantitative value on hotspots. I mean, how good are hotspots from a business perspective, for example? I decided to do, I studied a bunch of different things, but one property that fascinated me earlier on was to find, is there any relationship between hotspots and defects? And the reason I focused on defects was because bugs, they have this really fascinating property. Bugs tend to cluster. Bugs like each other. So what I did was I basically study the relationship between hotspots and defects. And there are several ways you can study this, right? One obvious way is, of course, to measure where are the hotspots right now, and then you wait and see where will the bugs be. That's pretty time-consuming, isn't it? And I want to evaluate many different code bases. So I decided to do something easier. I decided to travel in time. Very, very easy with version control history. So I basically took a bunch of code bases, rewinded their Git history 6 months, 3 months, 1 year, and then I measured the hotspots, and then I looked at where have the future bugs been. And I studied a bunch of different code bases. I just want to show you one example here of a really strong pattern. So what you see here on screen is Hibernate, a well-known object relational mapper written in Java. And when I did this case study, it's many years ago now, but what I found was really, really fascinating. I found that the hotspots correctly identified 7 out of the 8 most defect-dense parts. What's even more fascinating was that the hotspots only made up 4% of the code, yet those 4% were responsible for 72% of all defects. So what this means is that if we use hotspots to guide our testing efforts, then we're very likely to catch a large, significant bunch of our defects. Now, one tip to simplify things like defect mining using this behavioral code analysis technique, these forensic techniques, all you need to do is to maintain one single rule. Please remember to always include a reference, your tickets or issues in the commit messages. So you see an example here in the middle, right? So we have 2 tickets referenced here. Because if you do that, not only will that give you requirements tracing in general, which is always a good idea to have, right? It's always important to know why was this piece of code written or changed. But it also makes it really, really easy to separate out, is the code because we develop new features, or is it because it's a defect magnet? So we can use that to classify hotspots. So if you want to get serious with these techniques, this is something I highly recommend. And the process of inserting an issue stamp can, of course, be automated and even verified using things like Git's pre-commit hooks. Now, before I move into the last part, I want to point you to some of the available tooling. Before I do this, you have to remember that this is still a pretty young space. This is still an evolving field. And in fact, when I started to work with these techniques, there were no tools available that could do the kind of analysis I wanted to do. So I had to develop my own tools. And I have open sourced my first tool suite. It's a tool suite called CodeMat. So CodeMat is a simple command line tool that can calculate hotspots and a bunch of other metrics, the social metrics that I'm going to show you soon. And CodeMat has some limitations, but it's an easy way to get started. So if you're interested in this, then please check it out on my GitHub page. It's entirely open source. What I've been working on over the past year is the evolution of those techniques, and I call them CodeSyn. So CodeSyn automates all these steps. It also includes things like automated code health measure. And CodeSyn is available both in an on-prem version, which you can run on your own laptop or something, as well as CodeSyn.io, which is the software as a service. And CodeSyn.io is entirely free for open source projects. So if you like these techniques, please consider to support CodeSyn. Finally, and I covered this a lot in my latest book, I find it truly fascinating how much you can do from just a command line. So this might look a little bit overwhelming, but if you break it up and take it piece by piece, it's actually not that hard. Because what this command does is that it calculates on a file level using just a Git client. So you can get really, really far with that if you just want to verify something really quick. All right, I'm going to put up the links to the tools at the end as well. But now, before I take time for question, I really want us to travel beyond code, beyond hotspots, and see how we can predict defects with behavioral patterns. And I want to talk about our mental models of code. That is, how we perceive a code base and how that influences correctness. And I want to do this via a case study on Roslyn. So Roslyn is it's an open source project from Microsoft. It's one of Microsoft's flagship open source projects. And Roslyn is basically a compiler platform. That means Roslyn is a framework that you use to build tools for .NET code analysis and stuff like that. And what's fascinating about Roslyn is that it also includes 2 compilers itself. So if you look carefully at this visualization, you see in the lower right, you see there's a compiler package. I'm going to zoom in on it now. And there are 2 different compilers in it, the Visual Basic compiler and the C# compiler. And what's fascinating about those compilers is that the Visual Basic compiler is written in Visual Basic and the C# compiler in C#. Now, Roslyn is a gigantic code. What I have on screen here is 5 million lines of code. And even here, at the highest level view, we can see that there seems to be a very interesting hotspot in the C# compiler. Let's zoom in on that and let's investigate the crime scene. So it turns out that this hotspot in the C# compiler is actually a test suite. It's a test suite called the Nullable reference type tests. And the first question, and I'm saying this because this is one of those questions I get all the time when I present these techniques. And that question is, but should we really do a hotspot analysis of our test code? Isn't it enough to restrict it to application code? And I find it so fascinating because I have to tell you that over the past years, I analyzed hundreds of code bases, right? And I have to tell you that some of the worst technical debt that I ever found was in the automated tests. And I think the reason for that is because when we developers, when we write the test code, I mean, we tend to make a mental divide. On one hand, we have the application code, where we know this is vital, it's important that we keep it clean, simple, and easy to evolve. And then on the other hand, we have the test code. And most of the time, we're happy if we get to write any of it at all. And I think that kind of questions kind of highlights that mindset. And to me, this is really, really dangerous. Because if our tests lack in quality, or if we accumulate technical debt in our tests, they will hold back our overall efforts and make the whole system, including the application code, harder to work with and more risky to change. So always make sure to cover your tests with hotspot analysis too. Anyway, let's look a little bit deeper at this test suite. We can look at the code and see that the Nullable reference type tests is a single file with 93,000 lines of code. 93,000 lines of code. Is that a lot? Well, to put it into context, I would like us to look at the Apollo 11 guidance computer, the software that actually brought humankind to the moon, right? The source code for the whole Apollo 11 guidance computer is 115,000 lines of code. And I have to say in fairness that Apollo 11 was implemented using machine code, right? So it probably equates something like maybe 20, 30,000 lines of code today in a high level language like C#. So this is actually fascinating. It turns out that implementing and testing nullable reference types in C# is actually a harder problem than landing on the moon. Who knew? Anyway, is it a problem to have 93,000 lines of code in a single test suite? Yes, I would like to claim so, because what I would be concerned about is the social dimension of code. So let me explore that for you. So to the left, you see the hotspot visualization that we just looked at. To the right, you see a different kind of analysis. This is something I call a coordination map. It's something I use to measure developer congestion. So what do I mean with developer congestion? I simply mean that I measure how many different developers have contributed to each piece of code and how diffused, how fragmented are their efforts. So I basically calculate that using the tooling I showed you earlier, and then I weight it together to a normalized value so I can find the worst possible coordination bottlenecks as seen from the code. And what we see here is that there's a very strong overlap between the top hotspot and the most congested module. And this is very, very common for large hotspots. And this relates to what I talked about earlier. The reason a test suite grows to 93,000 lines of code is that it does many different things. It tests many different behaviors. And that means it has many reasons to change. So now suddenly it will attract more developers potentially working on different features and stories, but they all end up in the same parts of the code. And this is important to know about because factors like developer congestion and high coordination in code are some of the best predictors of defects. So I like to end this by showing you and pointing you to some fascinating research on the social side of code. And I have much more details about that in the references I'm going to give you. So let's look at the first piece here. The structure of the development organization is a stronger predictor of defects than any code metrics. So that means we don't even have to start by looking at things like cyclomatic complexity and other complexity metrics. The social side of code, if we're after correctness, if we're after predicting defects, factors like developer congestion are much, much more important. And this is kind of confirmed in the second study here, the one in the middle, that says that the risk that the commit produces a defect increases with the number of developers who have previously worked on the code. And I'm going to come back to that really soon. I want to point out that the third quote here kind of clarifies that this effect is something that we have even with a strong culture of quality peer reviews. And in particular, this research paper looked at the Linux kernel development, and the Linux kernel is well known for its high quality peer reviews. But they found out that organizational factors like developer congestions, number of people touching a piece of code, still held true. And not only could it be used to predict defects, it can also be used to identify more severe defects, defects that could have security implications. So the organizational factors are really, really important to master, measure, and be aware of in any large-scale software system. So why do you think this happened? Why are organizational factors so good predictors? It all ties back to the mental models that I mentioned a couple of minutes ago. Because social factors influence how we perceive a code base. So to me, in my role as a developer, if I'm working a piece of code, I never ever have a perfect representation of that code in my head. What I have instead is a mental model of what the code looks like. And it's an imperfect mental model, just like all other models. It's simply something that let me take something as detailed as code and squeeze it into my working memory. And it turns out that the more developers we are working on the same parts of the code, the harder it becomes to maintain those stable mental models. So imagine that we're writing a piece of code ourselves today, and 3 days later, when we want to change it the next time, 5 other developers have been working it in the meantime. So now I'm making changes based on a largely outdated mental model. So it's no wonder that things go wrong with heavy developer congestion. So I've come to the end of this presentation, and what I wanted to do here is want to present some techniques that can help you get situational awareness. And that situational awareness of how our code evolves and where its weak spots are and where the potential problems are is something that we can use to direct our testing efforts to the part likely to need them the most. And I also want to show you that behavioral code analysis, that I call this collection of techniques, is something that goes way beyond code. It's all based on identifying human patterns, developer patterns. And we have seen that those organizational facts are actually better predictors of defects than any properties of the code itself. And I find that fascinating because organizational factors are completely invisible in the code itself, right? So it tends to be information that is largely overlooked and typically not included in a software project. So this could be your secret weapon. And if you want to dig deeper, I want to leave you with a number of references here. I have my new book about it, Software Design X-Rays, where I cover hotspot analysis, developer congestion, and many, many other behavioral code analysis techniques, including some practical exercises on real code bases. So if you dive really, really deep, then I recommend having a look at Software Design X-Rays. You can also take a look at the tooling at Codes.io and run some analysis there. There are also some interactive results of large-scale code bases that you can explore to learn more and see those patterns yourself. And I blog regularly about this at mpr.com as well as at Tornhill.com. And now, before I leave time for questions, I really want to take this opportunity and say thanks a lot for spending this virtual session with me. Thanks for your time, and may the code be with you. Thank you.
Well, thank you, Adam, for your talk. We've got a couple of questions. Let's start. So, first of all, question from Alexander Shevchenko. How to work with refactoring and hotspot calculations? What if some components move out of file? Should we consider this movement somehow? Is it better to calculate hotspots based on code artifacts, classes, methods, etc.?
Yes, that's an interesting question. So I didn't cover this here. I had other sessions where I go into that topic. But basically, hotspots, the very concept is orthogonal to the level you measure on. So you can have hotspots on a file level and an architectural level, as I showed you here. But you can also calculate hotspots on a function level. And that technique is something I call hotspot X-rays, which is why my book is called Software Design X-rays. So it's a bit more complicated in this, but it's something that often pays off, in particular if you want to do refactorings, because the hotspots that you tend to find, they can, quite often, they're pretty large files, right? There might be thousands of lines of code. And to schedule a refactoring for 1,000 lines of code is simply very high risk. What's likely to happen is that the developers responsible for that, they're going to branch out, they're going to spend a couple of weeks on that branch, and they might never, ever be able to merge it back, because in the meantime, there has been so much development activity on the main branch. So using a technique like X-rays, where you calculate hotspots on a function level, can give you a very specific starting point for what to refactor. So you can make it actionable by breaking down the refactorings into small and well-defined chunks. So I hope I managed to clarify.
Okay, before the next question, one question from me, continuing to the first one. Am I right that after every refactoring which splits code base to smaller parts or extracts some artifacts, we should redo all hotspot analysis?
Yeah. In fact, I on my system, so I use these techniques on my own code, right? So we run hotspots every single day. And the larger the organization, the more frequently you want to run it. So at least once a day. And the thing is that even if you have a file and you start to split it or something like that, you can usually trace the content. So Git is pretty good at rename track. It's pretty good at tracking moved content. So you don't really lose information. You can pretty much figure out that this piece of code is something we extracted from this larger file, and then we refactored it, and now it looks better. So when I do this in practice, I tend to emphasize trends over absolute values. So I usually don't care if something has a semantic complexity of, what do I know, 120, right? It's not that interesting. What's interesting to me is that it gets better over time if it's a hotspot. Did I manage to answer the question?
Yeah. So the next question from our chat, what tools would you suggest to use to find hotspot in the code for beginners?
Sorry, what tools?
Yes. What tools would you suggest to use to find hotspots in the code for beginners?
So for beginners, I would. It depends a little bit on how you have your code. If you have it on GitHub, you should definitely check out the codes in IO, because it simplifies a lot of that stuff for you. It comes with the visualizations. You could also have a look at CodeMat. So CodeMat is good to give you a head start. There are some limitations with CodeMat. For example, it doesn't track renamed content, and it doesn't come with out-of-the-box visualizations. But any one of those would be a good start. I think that using the Git client, like I showed you, it's a little bit too low level. It's fascinating to do a quick experiment on it, but it's usually easier to use one of the other solutions.
Okay. Adam, following the next question, what is the largest code base which you've tried to analyze? How many millions lines of code, or 10 millions, 100 millions?
So the largest code base I've ever analyzed was 120 million lines of code.
Wow.
And in all fairness, it's gigantic. But in all fairness, that code base, I cannot go into much detail about it, but in all fairness, it contained a significant amount of open source code as well. But maybe half of it was actual application code. And then analyzed a bunch of other code bases between 30 and 40 million lines of code. So that's where I think techniques like this, it's absolutely fascinating, right? Imagine doing this manually, picking up 30, 40 million lines of code and trying to make sense of it. And with a hotspot analysis, within 30 minutes, you can basically tell that, all right, this is where most of the issues are. It's really a superpower. That's why I'm trying to push it to you.
So the largest is 120 millions, and half of it it's merged open source libraries or something from open source which can be handled by something else. And the second one is 40, yes?
Yeah,
14.
a bunch of them around 40. Between the 30 and 40. Yeah.
Okay. Wow, cool. And you said that it's
pretty large, I think.
30 minutes to analyze 120 millions of the code, lines of the code.
Yeah. But then I used a commercial version of CodeSyn where we spent a lot of time optimizing it for quick feedback, because it's basically like it's data analysis at scale, even if it's version control history. I mean, those repositories can be really, really big. So there's a lot of challenge in making it fast. But it's absolutely fascinating. I really love to explore code bases like that. And there are not that many. The largest open source code base I've analyzed is the Linux kernel, which is right now, I think, around 17, 18 million lines of code. So it's also a code base. And it's hard to come across larger open source systems. I think from research, we know that I think it was Windows Vista that was around 50, 55 million lines of code, which was at that time known as the largest commercial code. So always keep that in the back of your head. The complete Apollo 11 guidance computer, the computer that flew us to the moon, 115,000 lines of code.
Quite small for now.
Yeah.
Okay.
It's not that much.
Yes, we've got next question for you. Can I apply cognitive bottleneck method if it's named correctly for the rule of the 4 maximum enclosures in the auto-test scenario code?
So you mean the cognitive bottleneck, so you're referring to things like the deeply nested logic and that kind of stuff. Yes, so I do think you can do that, right? And I think it's the thing with deeply nested logic is that once you have identified it, it's usually pretty easy to refactor it. And you will see that quite often those different conditions, they kind of suggest like a separate sub-behavior. So it's quite often about something that you would like to extract. So I do think it makes sense. Then, of course, you have to be careful because it always depends on context. So I've seen code bases that take in modularization to the extreme as well. And then each method will be really simple in isolation, but the way they connect together is anything but simple. So instead of having local complexity, you now have distributed complexity in the coupling, and that's even worse. So it's always a balance. And using hotspots, you can figure out which parts of the code should I really prioritize simplicity in. Okay.
The next question, does rule of 4 max enclosures correlate with Robert Martin rule of max of 1 abstraction level in method?
Yes, I don't know. I haven't read anything from Robert Martin in a long time. Actually, just coming at this from a very different perspective. I'm not really starting from a software perspective. I'm starting from a psychological perspective. So I start to look at cognitive psychology instead to figure out where are the bottlenecks in our mind. And then we see how does that influence the way our code should look. So that's why I think this threshold of 3 to 4 it's a rule of thumb, right? I would never use it as a general rule, but it's definitely a rule of thumb because that's basically what you can keep in your head at once. So maybe that recommendation makes sense. I need to look it up.
Okay. The next
should
question.
I elaborate on something or clarify? Yeah.
Okay. The next question: what is the most widespread type of crimes in code bases which you've seen?
I have to say it's very different, right? So what I tend to see, it's a fairly common problem, is that we as an engineering community, we tend to underestimate modularity. So you kind of often see that, and I find it fascinating, that once you identify those hotspots, right, since you have version control, you can easily trace their evolution and see how they looked a couple of years ago. And what I see is that any issue that I find today tend to be exaggerated many, many times. And quite often it's a lack of modularity, simply stuffing too much stuff into one place. And I found that lack of modularity is something that you can find on all levels. You can find it on the file level, which is a little bit like what we talked about before with cognitive bottlenecks. And you remember the bumpy road code smell that I mentioned. You also find it, so that's the function level. You find it on the file level where you have multiple behaviors in the same file, which makes just grow and grow and grow over time. And you also tend to find it on a subsystem level or on a service level. And I simply think that it's also related a little bit to the organizational patterns, because when you have that more or less uncontrolled growth in responsibilities, means the modularity gets lower and lower. What I quite often tend to find is that often means that code is written by a lot of different developers. And by having a lot of different developers, I talked about the mental model challenges earlier, but it also basically means that with multiple developers, you don't have multiple people responsible for it. You have no one responsible for it. So I think lack of modularity would be my number one answer.
Okay, so next question. You've said a lot about Git. Is there any issues with other types of the version control systems? I don't know, Mercurial, SVN, whatever else. Or it's
no,
doesn't matter in the context of
this. It doesn't really matter, right? So you can do these analyses. I have applied hotspot analysis to Subversion, Mercurial, anything, right? And the only thing I haven't seen work is really old version control systems, like for example ClearCase, because ClearCase, if I remember correctly, doesn't really have anything that corresponds to something that looks like a MIT. It treats each file individually. But any more modern system than that, it will work pretty. The reason I use Git is, as in my examples, is because that's what I've been focusing my tooling on, simply because Git seems to have won out. And if you work in something else and you still want to use this tooling, you can easily set up an automated and temporary version to Git, right? So you can take your Mercurial or Subversion repo and easily mirror it to a read-only Git repo that you can then use for the purpose of the analysis. So it should work fine no matter what version control you have.
Okay. Next question. Adam, based on my experience of the hotspot analysis, which I've seen in Codebase, which I analyzed, two types of the places inside of the Codebase. First of all, it's some part of the Codebase which was written years ago and not changing for long years. And the rest of it is hotspots, which is constantly changing, and some parts of the code moving in, moving out. Somebody fix bugs, somebody adding some features. But let's talk about the former. I see the part of the code which is not changing for years. So there is no hotspots. It's almost dead. It seems like it's almost dead, yes? But it seems that some defects can be over there. Is there any tools, any other methods except the hotspot analysis which can bring some light to this part of the code base?
Yes. So there are multiple things. So first of all, I talked a bit about that when I talked about the sliding windows. When doing a hotspot analysis, it's really, really important to include a proper amount of data. And this is almost more based on, it's more an art than a science, right? You'll learn a number of heuristics after time, because it depends largely on how many, or how active project is, if it's in maintenance phase or new features being developed. But I almost never include a complete history to do a hotspot analysis. I typically limit it to information over the past year or something like that when doing an initial hotspot scan. So that helps you get better and more accurate data. The second thing is, yes, there are other techniques you can use, and they're related to what I talked about with the defect mining. So one thing I do is, if you have that link commits to your project management tools or issue trackers, then you can actually use that to calculate things like defect densities. And you could even take it a step further and see, depending on information you have, maybe you have a work log, so you know how much time you spent on each task. Maybe you can use that to also get the cost dimension on top of it, right? So even if something is not really a hotspot, if there are still several defects in that code, and those defects are expensive to fix, then that's clearly an area you want to know about. In my experience, scenarios like that are quite rare, because if code is truly problematic and hasn't stabilized, then it tends to be a hotspot, right? But there might always be edge cases, so adding that additional data can help shine a different light on the code base.
Okay, so we're almost done.
Yeah, thank you, folks. It was very nice discussion, and thank you for your presentation, Adam. You can continue talking and discussing in after this time slot in discussion zone, which is available in the Zoom meeting. So if you want to ask more questions, please follow that. By the way, you have to choose one kind of best question, or the question you prefer more. So we will winner of this question will get a prize. It is actually the book, so it's very useful, you know. So thank you very much. It's time to kind of close the first day of the conference. Thank you, Nikita. Thank you, Adam.
Thank you.
Thank you very much, and thanks for all the great questions.